It's very useful to write another relationship that explains the work done by the external forces. Now, thanks to how many ways of or how you are able to exchange the energy of your system by applying forces. First case, think to a mass M where you have forces around it, but these forces are not balanced. The forces, for example, in the left are bigger than the force on the right, and the force up and down are exactly the same. Okay? So you have a net force that goes in this direction. What happened to your system? It moves. But what kind of energy changes? Kinetic energy. Because we have that velocity increases, because we have an acceleration. So I call it C. The velocity increases in accordance with the acceleration. So thanks to forces applied to our system, we can have a variation of kinetic energy. Now, think to a similar problem, but now the forces are balanced in the horizontal direction and unbalanced in the vertical direction. So you have a net force in this direction. What happened? Not only, also the kinetic one. Okay? Because it moves in this direction with an acceleration, therefore you have both increasing kinetic energy and in potential energy. But we can write here delta Eg. Okay? Then the other part of energy. Remember when we said we have a force applied to our system. This system will be deformed. So another way to change the energy of our system is to have a variation in volume. But we said, remember, for the question that we observed before, with minus. Perfect. Okay, so this is the way to write the force, or better, the work done by external forces. But there is another part of work. Which one? There is another term here. I don't understand, sorry. No rotation, we are considering, okay, we can put also in the same way delta Ek by changing. No, another one. Oh, this is omega. Very important. Okay. We have also the effect of friction. A part of the work provided by the external work, the external forces, will be used in order to move molecules one near to the other one, in order to stress our system. So we have another term here that is the LWU. I don't know how you call it, but this is the friction work. The friction work say that a portion of the work provided by the external force will be used in order to compensate the friction. So we introduce a work. This work will be able to deform our system, accelerate our system, move it in the centrifugal or gravitational force field, but also able to provide the energy required in order to move our molecules one near to the other one. This is another very important relationship that takes the name of conservation of mechanical energy. This is the conservation of energy in the mechanical form. Okay? The difference between these two is that the first one is the conservation of energy. Stop. This is conservation of energy. All type of energy. Heat and mechanical. The second one is only for mechanical. It's very interesting to observe what happens when we combine these two. Before, let me write this relationship in another way, but very simple way, but more simple for the point of view of the form. Usually when I refer to Q, L, energy, the unit of measurement of this quantity are perfect. Joule. Okay? They are the energy referred to the Joule system, to the mass m. Usually we prefer to work with reference to the energy for unit of mass, because this is easier to manage. It's also simple to see the value for this one. So we define the quantity for unit of mass. Obviously, they are divided by m. The mass of our system. If you remember, we say that this property or this quantity are extensive. While these one are intensive. So the amount of our property or quantity refer to the Joule system, in this case Joule, or to a particular portion, a unit of mass of your system, intensive, Joule per kilogram. In the same way, we can talk also about the properties of our system. Do you remember, or better, are you able to give me a list of some properties of our system? What is the properties of a system? Oh, make me some example. Let me some name. Pressure. Unit of measurement? Better. Bar, megapascal, okay. Another quantity? Volume? Unit of measurement? No, volume is cubic meter, nothing else. Temperature? Unit of measurement? Or Celsius degree or Fahrenheit degree, etc. Other properties? Constant? But a property cannot be a constant. It's a property, it changes. A constant is a constant. Sorry? Enough. No, there are 1,000. Other properties? Eh? Mass? Mass. Other properties? Density. Unit of measurement? Other properties? But you said that we wrote before. You also called the other thermodynamic property. Enthalpy. Unit of measurement? Another property? The enthalpy is this one. Entropy? Unit of measurement? Other properties? Okay, so there are a lot of properties, no? But, for example, there is another, for example, the inverse of density is specific volume, unit of measurement. Okay, okay, some of these are intensive, other ones are extensive. Which one are intensive? Let me, in pressure, intensive or extensive? Pressure. Pressure is extensive. Is intensive because by changing the mass of the system does not change. No? If you have one box of gas or with 10 kilograms of gas at 10 bars, if you take the same another box with another max but always 10 bar, the property is always the same. This is intensive. This does not change by changing the mass of the system. Volume? Extensive. Temperature? Mass? Extensive. Density? Enthalpy? Okay. So the properties that obviously don't change by changing the mass are intensive. These are property of this type. The temperature obviously does not change by changing the mass. Always 10 Kelvin. Okay? Does not mind if you have 1 kilogram of 10 kilograms. And there is another important, very, very, very important things. In order to define the state of your system, what is a state? When we say we would like to define the thermodynamic state of that system, it means that in that system all properties are defined with only one value. No? We say, okay, The system of the state has a pressure equal to 10 bar, temperature equal to 333 Kelvin, enthalpy of, I don't know, 2,533 joule per kilogram. We have a list of properties, okay? For any of them, we have one value. That is a state of our system, okay? The question is, how many of these variables you have to define in order to be sure that the system is exactly that one? 2, 3, 4? Only 2. If you are able to define 2 intensive property, the state is totally defined. Only 2. Pressure and enthalpy, enthalpy and entropy, specific volume and temperature. Doesn't mind. A couple of them. And the other one? The other one can be derived by using physical relationships. So, for example, thanks to the gas, PV equal to RT. If you provide pressure and volume, you already provided the temperature. Okay? Same times for enthalpy. You already know that H is equal to Cp T plus a constant. If you provide the temperature, you also provide the enthalpy. So you need only 2 properties. The other one can be directly derived without problem. There are many physical relationships between them. Okay, so let me write, and this is very important because this is the 2 formulas that you have to remember. First law of thermodynamics, with reference to intensive quantity, QE plus LE equal to delta U plus delta E, kinetic, gravitational, and reference, system reference. So, centrifugal force. Conservation of energy in the mechanical form, LE equal to minus P dV plus delta EK G omega plus LWU. Sorry, I did something that is not correct. Okay, I wrote, no, okay. It's easier to do this. Okay. So this is correct, it's correct. Okay. You have to remember these 2. They can be also written in the differential form. Do you remember? But it's not so important. By combining these 2, we have another very useful relationship. Take LE, put it in the first one. You obtain QE plus LW. Then you can simplify the variation of kinetical energy, etc. You only have delta U plus the integral of P dV. In differential form is more useful as dQA plus dLW equal to du plus P dV. This is a very useful relationship. What does it say? Look, what do you have in the left part? You only have energy exchanged by your system. Heat and friction work. Okay? Now, to the right part, okay, internal energy, pressure, specific volume, what are they? They are properties. They are defined by the state. Okay? So it says, in the right part, the properties of your system changes. The state of your system change. Why? Look at the right. Because you are providing heat. It says that there is no difference from the point of view of your system if the heat is coming from QE or is coming from LW. No different. It's always heat that is coming. A part of it, this is your system, a part of it is provided by the surrounding. The other part is as a source in, no? LW is coming from the interior of your system. But from the point of view of the changement of the properties, there is no difference. They are to be summed. We have an addition. So the most important thing is the total amount of heat. The heat coming from the surrounding by heat exchanging, and the heat coming from the interior by degradation of the mechanical work in it. When you make this with your hands, you are able to see the effect of friction. But this is a heat. It's like a source of heat. It's a source of heat that comes in your system. It's inside, not outside. No? It's the degradation. And from the point of view of the system, it does not mind if this heat is coming from the surrounding or from the internal of your system. The only thing it is important is the total amount. This is a very, very, very useful relationship. By means of this relationship, or thanks to this relationship, we are able to perform our calculation in ideal case. What does it mean, ideal? Ideal? So, no L, no LW. And the real case, where the LW is different than zero. Well, thanks to this, we are able to, and to this relationship, we are able to do the calculation in both cases without knowing the value of LW. This relationship is always true. This relationship is true for ideal and real cases. But we don't have LW. Why? What is the effect of LW? In which term? Which term is related to LW? Which one is related to temperature? U. The effect of the real case, the effect of LW, will be here. Because LW heat your system and increases its temperature. You are not able to see it alone because it is in the variation of internal energy. When you separate the mechanical energy from the whole amount of energy, so separate heat from work, you see its effect. And usually we don't know how to calculate it. Or better, we can use this relationship in order to derive the amount of LW. Because no one is able, usually, to provide us a formulation for LW. We don't know it. It is a question mark, usually. Okay? So, ideal, real, all cases, this very important relationship. And there are particular restrictions for this representation, for this formula. Do you remember restrictions? Is it always, or are they always true? Or sometimes they are not valid? Are there restrictions for it? Okay, closed system, but it can be also applied to an open system. But the answer is restriction, yes or not? Yes or no? Do you remember some restriction for this kind of relationship? So in some case it cannot be applied, or you can apply this relationship always without a restriction. No, I said a few minutes ago. Reversible means ideal, LW equal to 0. Real means not ideal, LW equal to 0. And I said that we can apply this relationship in both cases. So the answer is no restriction. This relationship can be always applied. Always. Okay? No restriction. All problems can be studied by using this relationship. Okay? This is true for, or better, this is the formulation that we obtain for a closed system. At the beginning of the lecture, your colleague said, I remember, closed system and open system. And first law of thermodynamics for open systems. First of all, what is an open system? Okay. So, like before, we have a system of mass that exchanges energy with the surrounding, but also mass. Okay. So, if you remember probably the sketch of this system, usually as of this type, where you have a system, no? This is the boundary of our system, where we have a flux of fluid from the inlet to the outlet. We have a heat exchange, and also a work exchange that can be exchanged through a mechanical element that is able to interact with our fluid, with a fan. So we have here a rotational speed and a torque. Therefore, the power, no, usually in this sketch we put power, thermal heat. The power that we also indicate with a P, mechanical power, is equal to the product between the torque and the rotational frequency. Li is the, I don't know how my colleague call it, probably internal work or technical work. Internal work. What does it mean? Is the work exchanged by means of mechanical elements that are able to interact with our fluid. Li is different than Li, no? Because Li was defined like the full amount of work done by external forces. We have other external forces because we have forces here. We have forces here. We have forces also here, around the boundary. But this boundary, no, this one near to the wall, present a force, but in order to have a work, we need also a displacement. These walls don't move. Therefore, the work provided by the force along the wall is equal to 0. While the mass here is moved in our system, as well as the mass here is moved out. In this part with a work done by this pressure that push our fluid in our machine. Here with the pressure that break the mass going out. So in the LE we have to take into account the Li, but also the work done by these forces that usually we call displacement work. Is the work at the boundary. So they are a little bit different. Now, to write the relationships for the open system that can be used every way without restriction, make the problem quite complex. Okay? Therefore, we had a restriction in this case that simplify a lot the formulation. Do you remember the restriction that has to be added for open system? The flow has to be steady state flow. Or stationary. What does it mean? No time? What? No changing? No. In stationary condition or steady state flow means that if you put here some instruments able to measure pressure, temperature, density, enthalpy, entropy, blah, 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 they don't change. So this is the meaning of steady state flow. In any points of your system, you can look there and you are not able to see the effect of time. Pressure changes by moving from this point to this point. But always here and here you have two particular defined value of pressure, temperature. Not only the flow rate, everything. has to be constant. Okay? To say that the flow rating is constant, thanks to the, I don't know, a ball, where you introduce a flow rate constant. What happened? This is not in steady state, because you introduce the mass and the pressure in the ball increases. And probably the ball increases its shape. So the mass flow rate is constant, because but the mass will be increased in the system. Will increase in the system, like the pressure, the temperature, and enthalpy, and everything. So the meaning of steady state flow is that everywhere the properties, the state of your system in that point does not change with time. Okay? Under this particular restriction, the relationship for the first law of thermodynamic system will be very, very simple and similar to the previous one. So, let me write this relationship. First law thermodynamic for open system is QE plus Li equal to delta H plus delta E K G omega. Do you remember the previous one? First law thermodynamic for closed system. It was QE plus LE equal to delta U plus delta E K G omega. They are very similar. The only difference is this one and this one. This is always true, no restriction. This is true only for steady state system. There is another very big difference that does not appear as this one. These delta are a really different meaning. Are you able to explain them? These delta are totally different. No. Delta, what does it mean? When you see a delta in a formula, what does it mean? Change. Okay? Delta means change. Perfect. I'll write it. Delta of the general quantity, G, means, usually we say G2 minus G1. Okay? Generally speaking. Okay, when we applied this delta, the delta in the no restriction case, this delta here, the variation refers to what? It does not mind, because this delta is for U, this delta is for kinetic energy, etc. The question is not related to the quantity. Is related to the meaning of 1 and 2. With time. Because in this case, you have the system that changes from time 0, or better, from time 1 to time 2. With heat and work that is provided. So in this case, delta means the variation, for example, of the quantity G, U, for example, is U at time T2 minus U at time T1. Now, this delta in this case has no meaning because we are in steady state. So nothing changed with time. Okay? Delta here means from the inlet and the outlet. 1 and 2. Delta H is the enthalpy that we have at the cross section 1 at the output minus H that we have at the door 1. This delta refers to the position, inlet and outlet. This delta refers to time, end and beginning. So they are really similar, but really different. Okay? The approach is totally different. Tomorrow we will do some exercise and we will analyze something. Okay. Another thing that we have to do is the first law of thermodynamic, or better, conservation of law for mechanical energy in steady state condition. For open system, for closed system, we wrote LE equal to, in differential form, minus P dV plus D E K G omega plus the LW. Okay? We wrote this one. Now we would like to write for open system a similar relationship. Okay, well, it's not difficult because obviously the relationship that we wrote here, that is always true, no restriction, can be applied also when we are working in steady state. It is always true, steady state or not steady state. The second one, obviously, will be only for steady state. How we can derive it? By using the previous relationship. So, look here in the previous page. If you do the difference between these two relationships, you obtain that the difference between Li and Le is equal to the difference between delta H and delta U, because this, okay, can be removed. So you can write that dLi minus dLe equal to dH minus du. Okay? But do you remember the relationship between H and U? Both of them are state property. H is defined like, is related to U, plus PV. Therefore, you have that this is equal to the differential of PV. Okay, this is the definition of U. In other words, you can write that the Li is equal to the Le plus the PV. So the only things that we have to do is to use the formula that we obtained before for Le, make this substitution, and obtain the final relationship. It was minus P, is written here, P dV, plus d Ek G omega, plus del LW, plus the PV, that is P dV, plus V dP. These two terms will be simplified, and you have another relationship that is very, very similar. V dP plus d Ek G omega plus the LW. They are very different, very similar. Another time. The only difference is that. So it's very simple to remember that. Remember that by providing shaft work to a machine, you increase the pressure. DLI equal to VDP. No, in order to remember the sign. Here, by provide work from the external force to a volume, we decrease the volume, minus PdV. These are the only terms that we have to remember. Okay? And now we have all the relationship we need in order to perform our calculation. First law of thermodynamics, the system, the relationship for closed system, also called the Lagrangian form, will be used in net positive displacement machine. The other one for open system, also called the Lagrangian form, will be used for dynamic machines, because it's in that case we always can apply the restriction of steady state. Okay? You look very tired. Therefore, I decided that we do exercise, and you can, in this way, you can wake up a little bit. Very simple exercise. Try to solve it. Oh, better, we need only two information about the H and the U. Do you remember how you can evaluate the enthalpy variation and the internal energy variation? You can evaluate it in a simple case. We have a system. A system in a box. Okay? System in a box, the box is not deformable. In the box, we have the mass. The mass will exchange heat with the surrounding. Okay? Apply to this system the first law thermodynamic and relate QE to the variation of other quantity, variation of U, variation of H, etc. Would you like to do it with numbers? This is air, 100 joule, 1 cubic decimeter. Evaluate the variation of U. And the variation of H. Give me formula to write. So what formula you decide to apply? Okay. For closed system. Okay, so Lagrangian form. First of all, we have to write it. Q okay.
So in this case, we have to work because we're assuming that our system is a volume constant.
Okay, so let me write the other relationship.
So volume constant is 0.
Okay, now?
First one is equal to 0. Yes, second one also. Energy is not. There's no friction given, so.
The friction is not given, but you know if it exists or not? It's air. But LE is the work done by the... Okay, where are the external forces? Here. The system, does change its volume? No, because it's undeformable. Okay? So LE is equal to 0. The kinetic energy of the system, etc., it does not move. Okay, so you have that the variation of internal energy is equal to QE. Okay. It can be for real or not real. Doesn't mind. Okay, we have no restriction about that. But are we able to relate U to temperature? Yeah, but how does it define it? But what is CV? Okay, you remember C is defined like Q over dt. This is, the name of this is specificate. Okay, specificate. specific heat coefficient. This is the amount of heat. This is the temperature variation. Unit of measurement? Are you sure? This is heat per kilogram. Are you able to give me a definition in words, not in formula, for the specific heat coefficients? Allora, the amount of heat, okay. Okay, so is the amount of heat required from 1 kilogram of our system in order to be increased in temperature of 1 Kelvin or 1 Celsius degree. Perfect. Okay, this is the general definition of C. Now, we can define many C by changing the process, okay? Along a constant volume process. Quindi CV is equal to dQ over dt along a constant volume process. Before, a few seconds ago, we analyzed this problem. And we said in this condition, Q is equal to du. In this particular case, we have that du is equal to Cv dt. Okay? But, do you think that this is true only for this particular case, or it is always true? So it does not depend on the other properties. But, sorry, how many properties are required in order to define a state? 2. Here, I see only 1. So, the state can be, many different states can have the same temperature, but different, for example, pressure. 1 bar is one state. 10 bar is another state. 100 bar, another state, always with the same temperature. So in this particular case, I can say that it is true only for an ideal case, an ideal gas. I'm not sure, probably also for the other one. But continue. With a constant process, a constant pressure process, you can write the previous relationship, like before. Always refer to that system, but now the system is of this type, okay? So the pressure is constant. And we provide a heat. So by using the relationship to this problem, what we can write? Like before. This is the mass. So, first law, write it complete. QE plus LE equal to delta U plus delta A K G omega. Okay. And LE is equal to minus integral P dV plus delta E C K G omega plus LWU, and always equal to force ds. Okay? In this case, the force will be equal to P times A. Perfect. And the displacement? Okay, the additional stroke, this piece of stroke related to volume. Okay? So time C equal to PA V over A, V is the variation of volume, okay, as you suggest. So, in our case, QE plus P delta V. Always look for sign. LE is the work done by the external force. In this case, the external force are in this direction. The displacement is in this direction, delta V. P delta V will be a positive quantity, but LE has to be positive or negative? Has to be negative, because the force are against the displacement. So here we have to put a minus. Equal to, like before, delta U plus delta EKG omega. This is negligible because we consider two phase without movement. QE equal to delta U plus P delta V. What is it? P is constant. So we can put P
outside of
also inside. No? We can write delta PV because it's constant. Do you agree? And what is U plus PV? So this relationship is dH over dt. Then we have that the variation of enthalpy is the variation of Cp delta T. Okay? And now also, it is always true. Unfortunately, we only have one property here. This is true under some restriction. We have to examine that. Few seconds. Well, H is a properties, okay? In order to define a value of H, we need how many properties in our system? We said 2. One of these can be, for example, temperature. The other one, pressure. Okay? Oh, do you remember maths? When you have a quantity, a function of two variables, in order to analyze the variation of this quantity, you have to combine the variation in both variables. Do you remember the relationship? It should be. Try to remember. The H over dt at constant pressure time dt, as this is the effect on temperature, plus dH over dP at constant pressure no, sorry, at constant temperature, dP. Okay? This is the mathematical formulation. Okay? Now, if you analyze this relationship by using formula, etc., you can write this in a very simple way. This first term is our Cp dt. The second one is not zero. The second one is 1 minus beta t dp over rho, where beta is defined as 1 over v, the v over the p, no, should be over the t at constant pressure. So these terms say how our fluid changes its quantity, its volume, by changing the temperature at constant volume, at constant pressure, sorry. Okay? Now, when our fluid is a gas, an ideal gas, do you remember the relation, the state equation for the ideal gas? We wrote before. PV equal RT. So, evaluate beta for an ideal gas. Where? Here?
No, there. Delta equal to 1 minus 1 yes.
No, this is the meaning of beta. 1 over V.
Yeah. Should it be there minus sign?
No, without minus. In this definition is without minus. And if you write V, you have RT over P. By deriving V with respect to temperature at constant pressure, it is equal to R over P. Therefore, your beta is equal to 1 over V, the V over the T at constant pressure, RT. Scusate, sorry, this is not T, but P. Okay? But Vp over R is equal to 1 over T. So for an ideal gas, beta is 1 over T. 1 over T tau in T is equal to 1. So for an ideal gas, you have that dH is exactly equal to Cp dt, and also du is equal to Cv dt. In ideal gas. Now, we can try to apply the same relationship to an ideal liquid. What is the relationship for an ideal liquid? The state equation for an ideal liquid. The most simple relationship. So, density? Constant. Not compressible. So, means V equal to constant. So, beta is equal to 1 over V, the V over the T at constant pressure. Beta is equal to? Look, V is constant. The V over the T is 0. Beta is equal to? So dH for an ideal liquid is Cp dt plus 1 minus 0, 1, dP over the rho. DP over rho. This should be the real, so it depends of the liquid, of the fluid, but it's very important. Look the order, you have to be engineers. The first things that you have to do is to give numbers. The order of magnitude of Cp for a liquid. Things to water. They are very similar to water. Water is a little bit higher. The specific heat for water is 1. As the order of magnitude of some thousand. For water is about 4,000 joule per Kelvin. For oil can be 2,000, 1,800, but the order of magnitude is some thousand. The order of magnitude of density for a liquid, but for water, 1,000. For oil, so liquid usually has a density of the order of magnitude of 1,000. They can be 800, they can be a little bit heavier, but the order of magnitude is 1,000. So we have that dH is about 4,000 dt, or better, put delta in order to be plus delta P over 1,000. So when you analyze this relationship, the first things to do is to analyze the order of magnitude. Think to a variation in temperature quite small, 1 Celsius degree, okay? It means that this term will be about 4,000. In order to have this term comparable, how big has to be the variation in pressure? No, 1 bar, no. You have to put here 4,000 times 1,000. In this case, you have that these two terms are comparable. Okay? Because the order of magnitude of this is 4,000, the order of magnitude of this is... But how many Pascal you have here? 4 millions. And 4 millions are 40 bars. So, the effect of the changement in temperature in your liquid of 1 Celsius degree can be obtained by increasing the pressure of 40 bars. It means that the pressure has to be increased a lot in order to change a little bit the enthalpy. Only by increasing the temperature of 1 Celsius degree, we have many bars in comparison. So at the end, we can say that that relationship can be also applied for liquid. Obviously, we have an approximately. It means this will be true if the pressure does not change of 100, 500 bars. If you are working with our machine in our course, usually the pressure changes few dozen of bars. So we can use that formulas. if you study an injection system, a common rail injection system, for example, where you know the pressure are approximately equal to 1000 bar, in that case, the variation of enthalpy has to take into account also the effect of pressure, because 2000 bar are important. They can introduce a comparable effect. But usually, the temperature is the more important. So this is the reason why when you talk about the variation of enthalpy of energy, you said that Cp dt is the formula for ideal gas. For liquids, it's not correct. It's a good approximation, usually, but not correct. Okay? At what time we have to finish? One minute. At 50? What 40? At 40. So it's practically finished. Okay. Okay, see you tomorrow. Probably tomorrow we have to change the room. I don't know if we have to change the room at the beginning or after lunch, but surely we have to change after lunch.